Welcome to the 16th day of research discussion on graphs and groups.
We have Shohei Satake from Japan. He is a master's from Nagoya University and a PhD from Kobe University and currently a postdoctoral fellow at Kumamoto University. His major specialization is random graphs and spectral graph theory. So welcome Shohei, and you can start your talk.
Okay, so thank you very much for your introduction, and thank you very much for giving me an opportunity to give a talk on this research discussion on graphs and groups. So in this talk, I will briefly review some known results and known works on the automorphism or groups of the random graphs, and related some results in graph theory and related combinatorics. Okay, so start this one. Okay, so actually the study of the automorphisms groups of the random graphs is established by Erdös-Rényi in 1963. Okay, so we will mention this. Okay, throughout of this talk, let Z be noted a graph and V of G here. Okay. The V of G denotes the vertex set of the graph G. Okay, so let E of G denotes the edge set. Oh, sorry, edge set. Edge set of the graph. Okay, so then the automorphism of the graph G defined as a permutation sigma on the vertex set V of G, such that it preserves the adjacency relation of the graph. Namely, if the edge U sigma and B sigma is belongs to the edge set of G, if and only if the original edge UV is also the edge. Is an edge of the graph G. Okay, so of course we can find some trivial automorphism anyway whenever that is trivial automorphism, and that is a permutation fixing all vertices. This is trivial automorphism. Okay, and also later we will mention about some digraph cases, and in these cases automorphism is also defined in the similar manner as well. Okay, so let S with Z denotes the symmetry group on VZ, as that is a set of all permutations on the vertex set V of G. Okay. And then the automorphisms group of the graph G, which is denoted by auto of G, is defined as a set of all automorphisms of the graph G. Okay. Of course, this is a subgroup of the symmetric group SVG. Yes. Okay. So okay, we introduce symmetric graphs and symmetric graphs. Okay. So for graph G, let Z. We say Z as a symmetric if the automorphism group contains some non-trivial automorphisms, and okay. So otherwise, if automorphism group is trivial, in this case, we say graph G as a symmetric. Okay. Okay. So we will see some easy example. Okay, so these two graphs are graphs with 6 vertices, and okay, let's see the first graph G1. Okay, so this graph is a symmetric since actually we can find only trivial automorphism from this for this graph. Okay, and on the other hand, okay, so let's see the graph G2. Actually, this is a symmetric graph. For example, actually, automorphism group contains 3 non-trivial automorphisms. For example, we can find a non-trivial automorphism switching these 2 vertices here. This one. So involution switching these 2 vertices is clearly automorphism. So this is a non-trivial. This is non-trivial automorphism. So this is a symmetric graph. Okay. So, okay, let's see the question by Erdös-Rényi proposed by 1963. Okay, so they mentioned about, for example, symmetry of a graph is often measured by the order of structure of its automorphism group. So we have measured for some symmetry for symmetric graphs. Okay, so however, it is also known that almost all graphs are symmetric. That is, almost all graphs admit only trivial automorphism. In these cases, how can we measure its asymmetry? Okay, of course, for asymmetric graphs, always its automorphic group is trivial. I mean, the order is equal to 1. Okay, so in these cases, we need a new measure for asymmetry for asymmetric graphs. Okay, so to answer this question, Erdös-Rényi defines the degree of asymmetry of a given asymmetric graph G, like this. Okay, so let's LG denotes the degree of the symmetry of a graph G, which is defined as a minimum number of the size of the symmetric difference. Here, a large delta denotes the symmetric difference of the two sets. Okay, the symmetric difference of the H set of E of G and the H set of E of H, where H is a symmetric graph, which is a graph with a non-trivial automorphism and with same vertex set. Okay. This is a degree of asymmetry. Okay, so we should mention about this captures the measure of the asymmetry. Actually, first we can easily check that if a graph G is symmetric, then A of G must be equal to 0. And if A of G equals 0, then conversely we can also say this is a symmetric graph. Okay. So, okay, recall the graph G1 in the previous slides, and this is a symmetric graph with 6 vertices. Okay, so since this is a symmetric graph, the degree of asymmetry is positive. And okay, by taking the graph H, right, for example, this one. Yeah, this is H. Then we see that actually H is a symmetric graph, and we can compute the size of the symmetric difference between this H set of E of G1 and H set of E of H. Then we can see the degree of asymmetry of G1 equal to 1. Okay, this is example. Okay, so we are interested in how the degree of asymmetry can be large for general and vertex graphs. This is one of the interesting extreme questions. So Erdös-Rényi established the following upper bounds for the degree of asymmetry. That is, for every n vertex graph G, we have A of G as at the most n-1/2, where this symbol denotes the Gaussian symbol. Okay. Gaussian symbol. Okay, so this is Erdös-Rényi's bounds. Okay, so now we are interested in this bound is tight or not. Actually, this is a big open problem in this area. Okay, so actually Erdös-Rényi proved that the equality holds only if G is a certain strong irregular graph with these parameters. That is a strong irregular graph with n vertices and n-1/2 regular graph, such that for every non-adjunct, every pair of adjunct 2 vertices, such vertices have exactly n-5/4 common neighbors. Okay. And for every 2 non-adjunct vertices, these vertices have exactly n-1/4 common neighbors. Okay. So hence, actually, suppose equality of this inequality holds, then we see that actually the size of number of vertices should be congruent to 1 modulo 4. Okay. So in the below 2 pictures, we put some examples for SRG, or in this case, n equal to 20. I remember 29. I remember 29. Okay. So okay. Anyway, first Erdös-Rényi found that actually constructed strongly irregular graph with these parameters. Like this, which is called a Pele graph, constructed over the finite fields and the adjacency relation defined by the codec residues. over the finite fields. Okay. So, however, Erdös-Rényi pointed out that actually the graph, strongly regular graph, which is constructed, is symmetric. So, first, Erdös-Rényi conjectures that actually the inequality, this one, LG, is at most around n over 2. This is not tight. Okay. So, however, later, Paulus, for example, Paulus found that actually we have a strongly regular graph with these parameters, which is asymmetric. That is, which admits only trivial automorphisms. Okay. So there's a hope that actually this their inequality is tight. However, unfortunately, it is still not known that there exist some tight examples or not for even some specific examples like Paulus graphs. Actually, we want to compute the degree of asymmetry of Paulus graphs, but at least I don't know how to compute it. Okay. On the other hand, Borobash, there is a famous book by Borobash entitled Random Graphs. This is one of the standard textbook in random graph theory. And in chapter 9, Borobash conjectures that for infinitely many integers n, which is equivalent to 1 modulo 4, then there exists an n-vertex graph which is tight with respect to the Erdös-Rényi inequality. Okay. But this is still open. This is big problem, I think. Okay. So we explained actually we don't know actually Erdös-Rényi inequality is tight or not. However, Erdös-Rényi instead proved that their inequality is asymptotically optimal in this sense, in the following sense. I mean, for every sufficient large positive integers n, then almost all n-vertex graph G satisfy as the following inequality, which means that recalls that Erdös-Rényi inequality shows that actually the degree of asymmetry is at the most around n over 2. So actually, this lower bound is asymptotically optimal for sufficient large n. Okay, so their proof is based on the random graph Gn 1 over 2, which is a probability space consisting of all labeled n-vertex graphs obtained by choosing HH randomly and independently with probability 1 over 2. Okay, so okay, let's. So in this model, yeah, we have exactly 1, 2, 3, 4 n vertices. So we want to get graph and vertex graph randomly. Okay, so how we obtain graph randomly? So in this n vertices, there exists exactly n over 2 possible n choose 2 possible edges. Okay, so in each possible edges we select edges with probability 1 over 2, for example, or let's say this pair 1 over 2. So here we select some edges with probability 1 over 2, and okay, so let's see this pair 2, 3, and here we will not, for example, we will not select these edges with probability 1 over 2 like this. Okay, so we repeat this selecting by n choose 2 times, then we get some graph. Finally, we get some graph, n-vertex graph, okay, is this vertex set. Okay, so from this definition, actually, we can compute the probability of each graph, okay. So we compute the probability of each graph in this model. Is, okay, so what's this? Exactly, this is 1 over 2 times to the power of the size of h, number of edges, and the number of non-edges, which is n choose 2 minus the number of edges. Okay, so actually we have for each graph G n-vertex graph in this model, G has probability 2 to the power minus n choose 2. Okay, so this is a rough explanation of the random graph G n 1 over 2. Okay. Of course, you can instead set h probability 1 over 2 by replacing all real number between 0 and 1. Okay. Okay. So Erdös-Rényi proves that by using this random graph model, Erdös-Rényi proved that there is some constant C such that the probability of the graphs is such that the degree of asymmetry of G is greater than n over 2 minus C square root over n log n. And this probability tends to 1 as n tends to infinity. So by proving this theorem using random graph, Erdös-Rényi proves that's the above theorem. That's one. Okay. So now we know almost all n-vertex graphs asymptotically tight with respect to the Erdös-Rényi bounds for the degree, upper bounds for the degree of asymmetry. Okay. So this is the results of the Erdös-Rényi in 1963. Okay. Okay, so after their work, there are some subsequent works. Okay, so I can't introduce all related subsequent works, but I will introduce some of them. Okay. So later Spencer is in 1976 introduced the other notion of asymmetry, which is noted by B of G. Here, Spencer measures asymmetry by using the size of the symmetry difference of the two sets, namely the H set of the E of G and the image of the H set of E of G with respect to the permutation sigma, where sigma is a permutation on the vertex set of E of G, which is not identity. So as in the Erdös-Rényi's degree of asymmetry, we can see that B of G equals 0 if and only if G is symmetric. That is, G has some non-trivial automorphism. Okay. And there's a relation between the Erdös-Rényi's degree of asymmetry and Spencer's the measure of asymmetry. I mean, A of G is at least 1 over 2 times B of G. Okay. This is Spencer's result. And and Spencer proved by Provis method using random graphs appeared in the previous slides. So Spencer shows that for every sufficient large integer n, then almost all n-vertex graph G satisfies that B of G is at most n over 2 minus large O over square root n over log n. Okay. I think this is a mistake, so I'm sorry. I think this should be n. Sorry. Yes. So okay. But anyway, by proving this theorem, as a corollary, Spencer proves the Erdös-Rényi's theorem. That is, for every sufficient large n, almost all n-vertex graphs satisfy this inequality, which shows that Erdös-Rényi's inequality is asymptotically tight for sufficient large n. This is Spencer results. Okay. So there is other notions of asymmetry, which is proposed by Kim, Satake in 2002. Actually, they define the defect of the graph G, which is concerned with the neighbor of each vertex. Okay. This is also the measure of asymmetry. And if D of G equals 0, then G is symmetric, and the converse is also holds. Inverse is also holds. Okay. And using Provis method, Kim Satake shows that for every sufficient large n, then almost all n-vertex graphs G satisfy that D of G equal around 1 over 2 times n. Okay. In the Provis method. And actually, Kim Satake proved that established some result for random regular graphs. Actually, they proved that for every sufficient large n and the positive integer d, which is at least omega of log n, and which is at most n over 2, then almost all the regular n-vertex graph G satisfy that D of G is bounded by this theorem. Okay. So actually, D of G is much larger number. Okay. And then this is main result in this theorem. And combining this previous result, Mackey and Warren in 1984, actually they proved that for every integer d greater than or equal to 3 and at most n minus 4, then almost all d regular n-vertex graphs are symmetric. This was the open problem in random regular graphs established by, I think, Borbach. And yes, by using the defect the notion of defect, Kinosaku view settle this conjecture. Okay, this is the last instance of the notions of asymmetry. This is coming from the very recent work by Goldreich Vigdarsson in 2021. Okay, so let gamma be a non-negative real number. Then the graph G is said to be gamma robustly self-ordered if this inequality holds in these cases. Okay. So this, in this case, as in the Spencer's measure of asymmetry, the set they also concern the symmetric difference of the two sets, namely the H set of G and the image of the H set of E of G with respect to the permutation sigma, no identity permutations. Okay. So we can see that this is zero robustly self-ordered, and this is not gamma robustly self-ordered for every positive real number gamma. Then we can see that this is symmetric, and the inverse also holds. Okay, so this was introduced in terms of the applications to property testing in complexity theory, but I don't know detail. But anyway, this paper was published in the conference on the complexity theory. Okay. And interestingly, Goldreich Vigdarsson proves that there exist some deterministic constructions of omega and robustly self-ordered n-vertex graphs. So in some sense, they provided deterministic constructions of graphs with high asymmetry. Okay. I think this is also very interesting recent results. Okay, so finally, we briefly introduce some of our works, then concludes my talk. Okay, so we introduce several notions of asymmetry of the graphs, and in our work, we deal with some digraphs, tournaments and oriented graphs. Okay, these digraphs have been investigated in graph theory extensively. Okay, so tournaments is oriented complete graph. For example, okay, you see this complete graph, oriented complete graph with 7 vertices. This is one of the example of tournaments. And also, more generally, we will also focus on the oriented graph, which is the orientation of some simple graph, undirected graphs. Okay, this. Okay, so in our paper, we introduce the notion of degree of asymmetry for tournaments and oriented graph in the similar manner, and as in the Erdös-Rényi's paper. Okay. So now we are interested in some extreme cases. So how this degree of asymmetry for tournament or oriented graph can be large? We are interested in this problem. And in 2017, I proved that for every sufficient large n, almost all n-vertex tournaments T satisfy that LT is at least around 3n over 4, like this. And actually, we also proved that this is asymmetrically optimal results. So we can't replace the constant reading constant 3 over 4 to other larger real numbers. We cannot replace it. Okay. So, and similarly for oriented graph cases, we also prove that for every sufficient large n, then almost all n-vertex oriented graph D satisfies that the A of D, the degree of asymmetry, is at least 2 over 3 times n. And this is also asymmetrically optimal. Okay, so maybe I have 2 minutes. Okay, so let's go to the summary of this talk. So in this talk, we introduced some notions of asymmetry, and we also introduced some results using random graph models. And finally, we briefly introduced some of our results about the degree of asymmetry for tournaments and digraphs. And yeah, since time is limited, we could not review all known works for asymmetric graphs, and this asymmetry, this notion has been extensively studied in many areas, not only graph theory, but also some complex theory, or in terms of the group graph isomorphism testing, like this. Okay. And this in this area, there are so many open and interesting questions, I think. So for example, again, we introduce this conjecture by Borobash for infinitely many, and there exists some n-vertex graph G, which is a tight example with respect to the Erdös-Rényi's upper bounds for the degree of asymmetry of FG. This is still open. And yes, and we also have other interest problems. For example, this is a random example. For example, can we improve some known results and other notions or symmetry? We can have such other notions. Actually, there are many open questions. Yeah. Okay, so that's all. Thank you very much for your attention.
Forum is open for discussion. Any questions or suggestions?
Shohei, I have a question.
Yes.
You yourself defined 3 types of asymmetry, right?
Yeah.
Measure of asymmetry.
Yes.
And for each of them, there should be some reason why they defined like that, right?
Sorry?
For each of these definitions,
yes,
there is some reason that they defined the measure of asymmetry like that.
Yes, as far as I know, there is no results about tournaments and oriented graphs. I think, this, is correct. It sounds. Can you understand? Yeah.
In each of the definitions,
yes.
I wanted to know why such a definition. Why is that the asymmetry is measured in that way?
So you wonder why we define this? Adaptive distribution.
Okay,
yes, this is a direct analog of the degree of asymmetry by Erdös-Rényi. Okay, let's recall the Erdös-Rényi's definition. Okay. Okay. Yes. So actually, we give a direct analog of the Erdös-Rényi's definition of degree of asymmetry. Yeah. Actually, we replace here by some tournaments of a oriented graph here. This original definition defined for the graph G, which is a graph. But here we replace here 2 tournaments or oriented graphs. Yeah. So we consider direct analog for tournaments and oriented graph of the original degree of asymmetry for undirected graphs.
Okay. I think I will better talk to you over email. I will ask this question. I think you didn't catch my question. So
can I just make a comment there, please, Vijay? I think in the Erdös-Rényi definition,
yes,
it's the smallest number of edges that you have to change to get from the given graph to a symmetric graph.
Yes.
So, you could think of a metric on the space of all graphs, the number of edges that you have to change to get from one to the other. So this is exactly how far away are you from a symmetric graph. Now, I don't know whether that's true of the other 2 definitions of degrees of asymmetry. It's certainly true for the Erdös-Rényi definition. Just how many steps do you have to take to get to a symmetric graph?
Yes.
Is that right? Yes, so certainly there's a good motivation for the Erdös-Rényi definition.
Yes, thank you very much.
I think there are no further questions. So today we have one more technical session. Our next speaker is Lavanya from IIT BHU. She completed her PG and PhD from IIT Madras in 2008. Her areas of interest are graph theory and network sciences, graph embedding, survivable routing in networks, spectral graph theory, algorithms and computational complexity, quantitative analysis of complex networks. She has a handful of papers to her credit and many invited talks. So on behalf of all participants of RDGG, I welcome you, Lavanya, to the session. You may please move with your presentation.
Thank you, Dr. Aparna, for this kind words. So actually, I should also add to my area of interest, algebraic graph theory, okay, so which I've recently started working. So now I can also say, happily I can say I also work in algebraic graph theory. So today our discussion, we will continue in line with our discussion on groups and graphs. So we've been introduced to different types of graphs which could be defined on groups. So today what we will be seeing is on this one of such class, which is the superpower graphs in groups, defined on groups. So this graph, superpower graph, was defined by Ashrafi and his team, Ali Reza Ashrafi and his team. So it is defined as, like, first of all, before I go, I want to talk about like what we are doing different from power graph. So as we know, in power graphs, we know two vertices are adjacent if one is a power of the other, right? Whereas here in superpower graph, what we say is we make two vertices of the group adjacent if either order of one element divides the order of the other element. Okay, so that is if A and B are adjacent, and G, that is either order of A divides order of B, or order of B divides order of A in the group G. So first it was called as order supergraph of power graph, and I think they still continue to call it that way, but I was not so comfortable with this order supergraph of power graph, so we just swinged it to superpower graph of the group G. Okay. And in some other papers, they have also referred to this particular graph class as main super graph of power graph. Okay, so it is just the different terminologies that are given, but we'll stick to this definition, this terminology of superpower graphs, okay, just to say that it's a super graph of power graph. So first of all, we have to observe that this superpower graph is a connected graph. It's going to be connected, and one simple thing is the identity element is going to be adjacent to all the elements in the group. Okay, so by this definition, so immediately we can see S of G is connected, and for the same reason we can also see that the diameter of this collection is 2. For this graph is 2. Okay. But sometimes we are also interested in studying the group, which is the proper superpower graph, which is obtained by deleting the identity element and also all those elements which are going to divide the order of the group, right? So all the phi of n elements also we'll try to remove, and then we'll try to study those collection of graphs also, just because we want to avoid this diameter 2, which is very it's a very nice property, but sometimes we are overwhelmed with that. So in distance related studies, we go for proper superpower graph also. So before we go further, I want to introduce to one more graph definition, which we will be using in the next couple of slides. So a quotient graph is a graph which is defined on another graph gamma, where the vertex set is nothing but a partition of the vertex set of the graph gamma, and two vertices in this partition are adjacent if and only if there exists a vertex in A and another vertex in B, such that they are adjacent in the graph, okay, in the original graph. So to talk about partition, most of the time we'll also relate it with an equivalence relation, so that as we know, since we are going to talk about group, we'll also talk about equivalence relation and partitioning the group based on the equivalence classes. So one such equivalence relation is that defined relevant to our superpower graph is that two elements x and y are related if and only if x and y are of same order in the group G. Okay, so this relation, you can see that if x and y are of same order, then it is going to partition the group G into equivalence classes where each class contains elements having same order. So that kind of helps us to go back to quotient graph, and we can try to study the quotient graph of the superpower graph, which helps us in some many ways for us. So with this, we'll go down and see some structural properties of this superpower graph of a group G. So suppose G is a group and P power alpha is divides order of G for some prime number P, and alpha is some integer n, natural number n. Alpha is in n. Then we can see that there is a induced subgraph which is a complete graph of this order P power alpha of S of G. So this is an interesting lemma. This kind of tells you, like, you can see that the superpower graph has a lot of cliques sitting inside the structure, and that also leads us to some other questions which we'll be posing. So to get a much more good feel about this, let us look into this collection. So pi e of G. Pi of G we will also denote. I missed to introduce here. Let pi of G be the set of all prime divisors of the order of the group. Okay. And let pi e of G be the collection of all element orders. Okay. So R1, R2, Rm are all element orders of G. And suppose if you look at the equivalence classes, so now you can see that each Ri is in order in G. So that means what, there are elements with this order Ri. So if you look at all those collection of vertices, that collection, that subcollections will form an equivalence class. Okay, and so that is going to lead us to our quotient graph. I mean, from the previous slide we can connect it, and we'll try to define a quotient graph on this collection. So now define a graph delta G with vertex set pi e of G. So the vertices of the given graph G is going to be pi e of G, that is R1, R2, Rm, and any two vertices here are adjacent if either R1 Ri divides Rj or Rj divides Ri for in general. Okay. So this kind of leads us to the fact that you can think of superpower graph as a join of this particular delta G graph, where each vertex is replaced with a complete graph. Okay, where complete graph on this omega R1 vertices, that is number of vertices of having order R1, or number of vertices having order R2, and so on. Okay, so each one will form a complete graph, you can see from the previous lemma. So it follows immediately that S of G is nothing but the join of a join of this particular combination of graphs. So now with this definition in mind, we'll come back to this definition after a couple of slides. So with this definition in mind, there are lots of results that were proven. First of all, we want to see what is the connection between the power graph and superpower graph. Okay. So if you go back, if I'm not wrong, I missed the authors here. The same authors, I mean, Asma Hamze and Ashrafi, they showed that in their first paper, the power graph of is nothing but the superpower graph if and only if G is a finite cyclic group. Okay. So this we can immediately see, one way will be quite clear or immediate, that if G is a cyclic group, then we just have to show that E of S of G, the edge set of S of G, is a subset of edge set of the power group, power graph of G. Okay. And to see that just from the order of the elements, we can immediately conclude that this holds. Okay. And for the other way around, assuming that P of G equal to S of G, we can show that G is a finite cyclic group, where by identifying each of the induced subgraph, they correspond to the normal subgroups in the group, and so that way we can see that it would be a finite cyclic group to end. However, I'm not giving the proofs in detail due to the lack of time, but the proof is quite straightforward for us. And similarly, S of G is complete if and only if G is a P group. So as we have already seen that there is an induced subgraph which is a complete, which is a clique, right? And if the one way we can is immediate again, if G is a P group, then we can immediately see that S of G will be complete, right? By P group we mean order of G is a P power K for some P and some integer K, right? So conversely, if you want to see for the other way around, suppose order of G has two distinct prime devices, say P and Q. Okay, then catch hold of those elements X and Y of those orders, say X is of order P and order of X is P and order of Y is Q, then we can immediately see that X and Y are not going to be adjacent. Okay, so if G has more than one prime divisor, then S of G is not complete. So that completes the proof again here in this case. So similarly, we can also see that S of G is Eulerian if and only if order of G is odd. Okay. So one immediate counterexample you can think of is, we know identity element is there, and so identity element is going to be adjacent to all the other elements of the group. Right. So if order of G is even, then we'll know that the degree of E, the identity element, is going to be nothing but odd. And so we know that S of G is not Eulerian if there are vertices with odd degree, right? So from there, again, we can conclude for the other way around, assuming S of G Eulerian, we can try to try to identify that every element will be of even order over here. And another interesting result is that S of G is also perfect. Okay, this can be proved again using Chudnovsky's result on a graph G is a graph gamma is perfect if and only if there are no odd cycles C5 or C5 complement. Right. So right from there we can use that result, and it can be shown that S of G is perfect. Okay. And similarly for planarity, there are some results here where S of G is planar if and only if G is the group is isomorphic to one of these groups. Okay, either it's an identity element or it is the Z2, the cyclic group on two vertices or two elements, or Z3 or Z4 or Z2 cross Z2 or S3. So again, coming back to the properties, you can connect the property or the characterization of planarity and the number of vertices here to identify the these groups over here. So these are some simple results that we have seen in the papers that are there, and there are many more results like this. Okay, not only S of G, they have talked about S of G star, S star of G, that is by deleting the identity elements from the remaining group S star of G, the graph, what is happening, whether it is planar, is it connected, and how well it is connected, and so on. So there are lots of such results. If people are interested, I'll put up the references towards the end. So another interesting in this line is the about the independence number. Okay, so as we have seen already that there is a very strong connection between the prime divisors of the order of group, okay, and having cliques as induced subgraph in the S of G. Okay, from there we can immediately see that the independence number, that is the set of all vertices which are no two vertices are adjacent in them, right? So the independence number is the maximum such collection we see. Excuse me. So alpha of S of G is given by this bound, which is bounded below by mod of pi of G, where pi of G is nothing but the set of all prime divisors of G, of order of G, and bounded above by pi E of G minus 1. Okay. So where this pi E is nothing but, as we had already seen, it is nothing but the set of all element orders of G. So an interesting fact here is that you can immediately see at least why these two bounds are going to hold good. Right? So suppose G is having, say, R prime devices, say P1, P2, PR. Okay. Or if you look at the prime factorization of order of G, that is equal, say, suppose I call it as n, then n can be written as, say, P1 power alpha 1, P2 power alpha 2, and so on, PR power alpha R. then we can immediately see that you pick up one representative element from each of these pi power alpha I, and those any two elements there are not going to be adjacent. So we can immediately see that the lower bound follows immediately. That is, we need at least r elements. We have at least r element which are independent in this collection. Right? And similarly, on the to look for the other side, if you look for the element orders in G, say we have there are k elements k orders are there, like A1, A2, AK are the element orders of the group G. Okay. Then if you form the delta group, delta graph using the pi E of G as we had defined before, similar to that, we can immediately see that S of G can be written as delta of each of the induced subgraph formed by those k omega of AIs. Right. So from there again we can see that the number of independent the number of pairs of independent vertices would be nothing but pi E of G minus 1, provided, like, if we look for the divisors within the collection A1, A2, AK, then we can try to see that it will be pi E minus 1. Okay, the number of elements in the pi E of G minus 1. Okay. So this is interesting, but where does the inequalities hold here? So if you see, the right side inequality is attained if and only if G is an EPO group. Okay, so the EPO group is nothing but if every element in this group is every non-identity element is of a prime order. Okay, then we can immediately see that alpha of S of G is going to be equal to mod pi E of G minus 1. Okay, and this is an if and only if condition, so it's kind of very well characterized result over here. And similarly, if you look for the lower bound is again attained by a group if which is of the form like the EPPO, that is, every element is of prime power order. Okay, not just prime order but prime power order. Then we can see that alpha of S of G is going to be equal to pi of G here. Okay. But this is not a characterization, this is just an if then result. So this kind of led to the next question, where are there groups other than EPPO groups which are going to satisfy this condition, right? So we can see that Z6, the group Z6, and if you look at the pi of Z6, we know there are two prime divisors, right? 2 and 3. So 2 is equal to pi mod of pi of Z6, and that is also equal to the independence number of S of Z6. But whereas we can see that Z6 is not an EPPO group, there are elements with order 6 also there, right? So therefore we can see that there is a gap here, and so Ashrafi et al, they propose this following question over here, that can we characterize the structure of groups where alpha of S of G is going to be equal to mod pi of G. Okay, so what is the structure of such groups? And there are some results which was given by Ma and Zhu in answering this question, but it is not complete and this problem still remains open. So for my focus, I want to go into vertex connectivity. So that is my interest, and we are working on this direction. So let me go into that. So vertex connectivity of S of G superpower graph. Okay. So to begin with, we'll do 3 collections here. One is the Zn group, and then we'll talk about 2 non-abelian groups, dihedral groups and dicyclic groups. And I'll try to wind up my lecture over here. Okay. So first of all, when n is a prime power, then we can see that if we look at S of Zn, then the connectivity is going to be equal to n minus 1. It is because, as simple as that, S of Zn is a complete graph, as we have seen already. So therefore, the connectivity is n minus 1. And if n is not a prime power, then connectivity is going to be at least phi n plus 1. Okay, phi n is the number of prime divisors of n plus 1. And here again, equality holds if and only if n is equal to pq, that is of the form product of 2 distinct prime numbers. So with this is already, I mean, for Zn, the results are already proved. So with this, what we have shown is that if G is a group of order n, which is not a prime power, okay, then suppose T is a minimal separating set of S of G, then for any element A and G, either the whole equivalence class containing A will be in the minimal separating set, or there is no element from that equivalence class. Okay, so this kind of tells us that the minimal separating set is going to be union of some equivalence classes in G, in a group G. As we can see, this is immediate, as we have already said that the S of G is kind of a join of complete graphs, right? So we have to remove the complete equivalence class to disconnect the graph. So with this, we also identify the size. I mean, what can we say about the size of the minimal separating set? So if n is not a prime power, then mod T, that is the number of elements in a minimal separating set, is going to be even if the group has even number of elements and if the T contains an element of order 2. And the mod T has odd number of elements otherwise, that is either order of G is odd or order of G is even and T does not contain an element of order 2. So another example is for the dihedral group. As I had promised, I'll just go over this. So as we know, the dihedral group is this group where we have the group generated by the elements A and B, where A power n equal to E and B square is equal to E, with this condition A, B, A equal to B. Suppose D1, D2, Dm are the positive divisors of n. Okay, then we can immediately see that S of D2n, okay, the structure of SD2n is going to be nothing but, look at the quotient graph of D2n, the delta D2nq, and blow up each vertex there by these complete graphs. Okay, Kn, K of phi of D1, phi of D2, phi of Dm. And if n is even, then it is going to be just Kn plus 1. Okay. There is in place of Kn, we'll have Kn plus 1. And this kind of tells us like we have lots of complete graphs, and this structure helps us in identifying how to disconnect. So we had to identify only those equivalence classes which will be a candidate for our element belonging into the minimal separating set. So as an alternate representation, I mean, sometimes looking at the devices is not so immediate. So we also looked at the other alternating definition here, which is given by your SD2N is kind of join of two blocks, where one block is nothing but the Hn, which is formed by the which is an n-vertex clique formed by all involutions of the form A power IB. And the superpower graph of the cyclic group of A. So for an odd integer n, we can immediately see that SD2n is formed by adding edges from every vertex of Hn to the identity element D2n in S of E. Whereas in the case of even integer n, we see that SD2n is obtained by joining every vertex of Hn to every even order element of the cyclic group A, okay, and along with the identity element. So just to give a feeling, we can see that, say if we are talking about n even, that is D12 here. So in this case, n is even. So we see that we have Hn is nothing but K6, and we have the cyclic group, the super power graph generated by the cyclic group of A here, and all the even order elements are connected to every element in K6. Whereas in D10, when n is odd, there is only identity element which is connected to every element of the clique over here, K5. And for when n is a power of 2, then it is immediate that SD2n is a complete graph K2n. So with this, we can see that the vertex connectivity of SD2n is nothing but equal to 1 if and only if n is an odd integer. Okay. And for when n is also not a power of 2. And similarly for even integer n, when for any n greater than or equal to 6, we see that the connectivity is given by at least phi of n plus 1 elements are needed to be removed. As we know, phi of n is the number of devices of n over here. So we need to remove at least these many elements to try to see if they can be disconnected. And in fact, this bound is tight if and only if n is equal to 2p. And again, one more thing is that any minimum separating set T dagger for this SD2n does not contain elements of order 2. Okay, so elements of order 2 will be at least n plus 1 will be there. So we will that will not really give us the minimum separating set over here. And similarly, the first we have discussed about the lower bound. So to give an upper bound, we also identified that if n is of this form, okay, so in general, any even integer, if we choose, then we can see that there exists a minimal separating set T of this size. Okay, and connectivity is going to be, we know that at least we know this, there is one set whose removal is going to disconnect the graph. So K of SD2n is at most less than or equal to T. Is at most this size of this T. And also this bound is tight again. Why it is tight? If you choose n is equal to 2 P1 P2, we can see that mod T is going to be equal to, given by this expression over here, phi n plus phi P1 plus phi P2 plus 1. And so that is also the connectivity of SD2n in this case. And so combining these two results from the lower bound and upper bound, we can see that the connectivity is bounded between phi n plus 1 and this mod T over here, this expression 2 over here. And another example, which is the dicyclic group. So even though dicyclic group and dihedral group look similar, but they have a very different structure for the superpower graph. So T4n is our dicyclic group with this definition where a power 2n is identity and a power n is equal to b square. Right? And the superpower graph ST4n can also be again written as the A join of this particular graph, delta T4nq, the quotient graph of T4n with this set of complete graphs. Okay. So again, alternatively, if we try to look into this structure, we can see that if each of this equivalence class is a complete graph over here, so the structure is going to look like this for ST20, that is when n is equal to 5 and n is equal to 6. So with this, I'll go directly to the connectivity part. So as we can see here, if we delete the equivalence class containing identity element and a power n, okay, then we can see that this will disconnect the graph over here, as we have a power n by 2 or b in the case of n odd case over here. And similarly over here also, we'll see if we delete this equivalence class of e or a power 6, this will disconnect this particular equivalence class from the rest of the graph. So this kind of led us to the next result. So the first thing is that if we want to talk about a minimum separating set, again, this equivalence class of B is not going to be contained in our minimum separating set. And for any positive integer, connectivity is going to be equal to 2 if and only if n is odd. In the case of dihedral group, we saw it was equal to 1. In this case, it is equal to 2. As we need to remove at least 2 elements, a power n and identity elements. So we need 2 elements in this case. And similarly, we started with n equal to 2 times p1 power alpha 1, p2 power alpha 2, pm power alpha m, and then another generic case where 2 power alpha we can consider. So in this case, again, connectivity is given by this bound over here, where upper bound is equal to n and the lower bound is phi of 2n plus 2. Okay. So again, these bounds are also tight, where lower bound is attained if and only if n is 2p, and upper bound is attained when n is equal to 2 times p1 p2. And similarly, the generic case, generic integer, even integer, any even integer if we take, then similar result, similar to the one before, but a different expression is there. So connectivity is bounded between these two expressions here. So with this, we talked about two non-abelian groups. So we have also tried to study some abelian groups, but the work is still pending. So I'm not going to go further into this. But I just want to point out this result, which was again proved by Ashrafi and team, where two groups, if G1 and G2 are two finite groups such that order of G1 and order of G2 are co-primes, then S of G1 cross G2 is nothing but the direct product of S of G1 cross S of G2. Okay. So this kind of leads us into the finite abelian groups case, where we can use the fundamental theorem on abelian groups, and we are trying to extend this to any generic finite abelian group case. Okay. So this result is still kind of incomplete, so I just want to just point out that we are still working in this direction. So where connectivity is at least T times phi of n1 plus 1, where n1 is the largest order element and T is the number of copies of this Zn1 inside the group. So with this, let me, I think I've taken already enough time, so let me stop over here. So to understand the connection between a group and superpower graph is what our main motive is. And in this direction, we can also see that if you are interested, you can see other results on automorphism group of S of G. For several specific groups have been proved, like dihedral groups, semi-dihedral groups, dicyclic or sporadic groups, etc. And also there are some results on the Laplacian spectrum and the spectrum of this S of G, and there are also results on graph polynomials, which was computed for S of G. And currently we are now working in superpower graphs of abelian groups and some non-abelian groups, as I just gave a couple of results here on connectivity. So we hope we could combine or find more combinatorial conditions on superpower graph corresponding to group properties. Okay. So with this, let me stop over here, and some references, as I had mentioned, which is given by Hamze and Ashrafi here. There are some papers. And these are the papers where we had discussed our connectivity results, and all these papers are communicated, so it's all under in pipeline. Okay. And the Ma and Zhu paper, this is where they have tried to answer the problem in relating to the independence number. Okay. And at this point of time, I'll take a minute to advertise that one of our papers with Professor Tamilchelvam and Professor Cameron is going to come up, which is a survey article, and it has lots of open problems for interested students and researchers. So this will be published in maybe by this month, I guess. So that's for your information. Thank you, and any questions?
Lavanya, can you please take some 4 slides previous to this?
Sure. Which
You have
slide?
looked at the problems. Yeah.
This one, yeah.
So this computation of graph polynomials for SG, you mean something like this what's called matching polynomial, independent polynomials, those notions are there.
Yes, yes.
So that is being found in the case of SG, isn't it?
Yes, yes.
So it's already done, or you are just suggesting as problem?
No, there are some polynomials they have studied. So there is a paper, if I'm sorry, let me just go over here to show you this. Some remarks on the order power graph of a finite group. So in this paper, they have studied some graph polynomials. And there is also one more paper, again, the same authors, they have studied on the graph polynomials of the power graph and its supergraphs for finite groups. So that was a preprint, but they have studied some dependency polynomial and independence polynomials, some 3-4 types of polynomials they have studied, along with the chromatic polynomial, I guess. So
I see. So can you please send me that these details and other ones? And
yes,
also this
sure.
spectral Laplacian and ordinary spectrum also is under study. No.
Yeah, they have studied the spectral and Laplacian spectral properties for specific types of groups, again dihedral, dicyclic. There's V8 group. V group is there, so that V group, and then some sporadic groups, nilpotent groups. So they have made some extensive study there. If you want, I can send these papers. Yes.
Yeah, fine. Thank you.
This is of diameter 2. It's a very dense property.
Yes.
Naturally, people will be interested in complement. Are there anybody who is looking after the complement of S of G as well as P of G?
Actually, we had studied the complement of conjugate graphs, because again in conjugate graphs also there is a very nice structure that complement is like multipartite graphs. Like it's so there we are trying to study the complement part, but not for the superpower graph.
Yeah, that's what my concern. Here again in S of G, because it is a delta G of some complete graphs, complement may also be something like multipartite.
Multipartite, yes. Yeah. In fact, it will have the independence number. That many multipartite sets will be there.
Maybe one has to look into that, but connectivity may not be ensured for the complement.
Yeah, connectivity may be difficult.
It's a worthwhile problem that when it is connected, complement is connected. I don't know.
Maybe we have to look into the complement of bar graph, that is deleting the identity and all the phi of n generators.
Yeah, definitely one has to. S star of
Otherwise,
G
it will be disconnected, obviously. Yeah. So,
S star
apart
of G
from that, yes. Okay, so let me stop presenting here.
So, I think there are no further questions. So let me thank both the speakers, Shohei Satake and Lavanya S for your valuable time and for the wonderful talks. The next session will be on 21st July. Sriparna Chattopadhyaya will be talking on minimal cut sets in the power graphs of finite nilpotent groups. So see you all then. Thank you.